Hey, good morning, everybody. It's Mr. Ainsworth, and we're going to get into a little study session and learn how to make a mind map on all the polar functions so that you guys be able to recognize what you're looking at when you're given the function itself and be able to graph it and determine all the characteristics of it just by looking at the coefficients, the a, the b, and the n values of any polar function here. So we're going to be talking about circles, roses or rosettes, and the limousons. And there are four different types of those. So what you need to do first is get this mind map from Canvas if you haven't done so already, or you can just freehand it and do it on your own. So depending on where you're at. Okay, and so the whole goal is to be able to graph a polar function, determine its characteristics without Desmos. All right, so let's get right into it. We're going to start off with the circles here. They tend to be the easiest. All right, and there's two types of circles. There's r is equal to a sine theta and r is equal to a cosine theta. Doesn't matter which one you do first. So let's start off with a sine, okay? And there's two types for each, okay, where a is either positive or negative. Okay, so let's start off with r at the top left here. R is equal to 3 sine theta. And let's analyze it first. All right, so here we go. All right, so first of all, a is 3. So when you notice this is r is equal to a sine theta, right? A is equal to 3, and guess what? That's a positive number. All right, and because of that, we know two things. First of all, 3 is the diameter, so I know the diameter is 3. Diameter is equal to 3 units, and since a is 3 and it's positive, it's going to be above the polar axis, okay? Above polar axis, and I just know that from experience because we went through the lesson, and we noticed that, we observed that, okay? On the second one, a is equal, or r is equal to a negative 2 sine theta. Well, that's going to be a little bit different, right? Okay, on this one here, if you want to know exactly what it is, you got to figure out where sine is max and sine is maximum at pi halves. So if theta is equal to pi halves, all right, what do we get? We get maximum radius, and r is equal to 3 times the sine of pi halves. Sine of pi halves here. The sine of pi halves is 1 times 3, which is 3, okay? And so you get 3 comma pi halves. 3 comma pi halves is on the graph, and that's why it's above, okay? So what we do is we just take a look at your a value. You go up 3 units on the y-axis or at pi halves, which is the same thing. Oops, pi halves right here. And then you draw your circle and just do your best job. Okay, just do a little sketch. Okay, it doesn't have to be perfect. And that's not perfect, but it's good enough. Okay, so the diameter is 3. And then again, a is positive, so it's above. It's really simple. And you can verify everything I say here with Desmos, okay? No problem. Split screen, like we always do in here. Let me just bring that up just to show you guys, because we did this in class. This is how we learned all the different functions in class. So split screen, determine your values here. I'll just do it one time. I'm not going to do this for all the functions, but because that's what you guys are supposed to do. All right, so let's turn on the circles here. Oops. It's in part 1, r is equal to a sine theta. So turn that on, and you turn a to positive 3. So let's go to positive 3 here. There we go, and you'll see it. There it is. There's your circle with diameter 3. It's symmetric about the y-axis right there because of the sine function. In fact, I forgot to write that down. We need to do that. Symmetry is a big deal. Okay, so symmetric about, you can say y-axis, or you can say the line pi equals pi halves. Okay, there you go. Now what's going on the next one here, r is equal to negative 2 sine theta. We've got similar things going on. It's still symmetric about the y-axis. Okay, but this time it's below. So a is negative 2, and that tells me that it's less than 0, and it tells me that the circle lives below, all right, below the polar axis. Okay, why? Well, if you take pi halves, actually, well, pi halves, well, if you take pi halves, let's do that. So theta is equal to pi halves. Okay, substituting the function, you get r is equal to negative 2 times the sine of pi halves. So the sine of pi halves is 1 times negative 2 is negative 2. And so negative 2 comma pi halves is on the graph. And so if you plot it, typically what you do on this function here, or this point in polar form, you go out 2 units, rotate pi halves, and then you reflect it. So it's not up 2 units, it's down 2 units. So it's down here. Okay, so there's a point on the circle here, and then of course you draw the circle. There we go. All right, so that point there is negative 2 comma pi halves. So above up here is 2 comma pi halves, but again, when the radius is negative, you reflect it across the pole, and now it's down 2 units. Okay, and that's what happens when A is negative. It's still symmetric. Again, talking about symmetry here, it's symmetric about polar axis. Making notes here. And these are all the things and characteristics that we observed in the lesson. And what we want to do in this little mind map here, well, not little mind map, it's going to be a big mind map, is just go ahead and review all the different facets, okay? All right, now let's switch to cosine, okay? There's two different possibilities here where A is positive and A is negative, so I just made up some values here. So starting off with for r is equal to 4 cosine theta. Here, A is 4, it's positive. But this time, for cosine, it's symmetric about the polar axis. So symmetric about polar axis. And if you want to figure out your start point, what you want to do is figure out where cosine's max, and that's at 0 and 2 pi. So if you let theta equal 0, all right, that means that r is equal to 4 times 1, which is 4. And that's why this function here, let me draw these axes a little bit better here. I don't have a whole lot of room here. So, okay, I'm just going to do it here. Okay, there we go. I'll call this 4 right here. And then, so let's plot this point. 4 comma 0 is right there, and then you just sketch your curve. Okay, goes through the origin too, by the way. Okay, because if you substitute pi halves in there, you get 0, and pi halves comma 0 is at the pole. Okay, 0 comma pi halves. So it goes to the pole right there. All right, now if A is a negative, right, which it is right here. So here A is negative 3. That's the left side. Okay, so once I see A is negative here and its cosine function is symmetric about the polar axis, it exists on the left side. Why? Well, if you substitute in 0 again, okay, you get r is equal to negative 3 times cosine of 0. Cosine of 0 is 1 times negative 3 is negative 3. And so you get to plot negative 3 comma 0. So instead of going 3 units to the right, okay, you got to reflect that across the pole, and it's only 3 units to the left side. All right, so right here. And then you sketch your curve. What's the goal? Okay, so it is a circle with diameter 3. So the first one, diameter is equal to 4 here. The absolute value of negative 3 is 3, and that's your diameter length. The sign of it, whether it's positive or negative, determines what side of the y-axis you're on. If it's positive, you go to the right. Negative, you go to the left. But they're both symmetric about the polar axis in this case. Okay, when I say polar axis, I'm talking about the x-axis here. Okay? Oh. All right, so that's all the information about the circles. Let's switch to roses. All right, and there's two types of roses here. One's with an even number of petals and one's with an odd number of petals. So we need to kind of investigate both. So I came up with two examples here. R is equal to 3 cosine of 2 theta. All right, so obviously here, let me put the form above it here. R is equal to A times cosine of n theta. So you can tell A is 3. That's pretty obvious. So A is 3. There's your petal length. Okay, and n is 2, and guess what? 2 is even, and that tells you that you have 2 times 2, or 4 petals total. Okay, all length 3. And there we go. And then here, cosine, since it's cosine, that tells you that the first petal starts on the at 0 degrees. So first petal starts at 0 degrees. So if you substitute that in, okay, so let's do that. So if theta is equal to 0, all right, what's r equal to? So it's going to be 3 times this cosine of 2 times 0, and 2 times 0 is 0, cosine of 0 is 1, times 3 is 3. So here r is equal to 3. So you can see that the first petal starts at, or the tip of the petal, excuse me, is at 3 comma 0. So we've got over here at 3, there's your tip. And then also for this function here, there's 4 petals. And let me see, let's do this. Let's do 360 divided by the number of petals, which is 4. That tells you that they're 90 degrees apart. Okay, you always take 360 divided by the number of petals, which in this case is 4. So up here, we're going to have another petal up at 3, and then you go left 3, and you got to go down 3. Okay, and you draw your petals. Let's do it. Okay, and then don't overlap the petals. Sound effects in. There we go. No, 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 no. Okay, there you go. There's a 4 petal rose. Now that happens when n is even. You double the number of, you double n, and you get the number of petals, and you go from there. Okay, now n may be odd. Okay, in this case. So in this one here, n is 3, a is negative 2. So a is negative 2 here. So again, you take the absolute value of negative 2, and that'll give you a petal length. Okay, so we have our petal length right there at 2. N is 3 though, this changes things. So n is 3, that's odd. And now we only have 3 petals. Okay, so when n is odd, like 3, 5, 7, 9, and so on, you have n petals. If n is even, you have twice as many petals. So it's a little bit different. Also, you take 360 divided by 3, you know there's 120 degrees apart. And then also, here you have to figure out where the first petal starts. Okay, so let me first petal starts at wherever n theta equals 90. So, okay, so where n theta is equal to 90 degrees. And so here we have 3 theta. Excuse me, 3 theta is equal to 90. Okay, so theta is equal to 30 degrees. So we have to start at 30 degrees there and then start rotating. Okay, so if we do that, let me see. So and we also go out 2 units. We got 2 units. Let me fix these axes here. I don't know what happened here. So, okay, so get some axes going. There we go. And we graph, 30 degrees, roughly right through here, and go out 2 units. And then rotate 120, so you got 150. So it's over here. And then another, let me see, add another 120. And then you're down here at 2 units. So here we go. So let's graph the petals. There we go. And they all intersect at the origin. Okay. Oh, Mm. Hmm. Okay, now those are the roses. Let's switch to the limacons or limacons. Limacons. It's French for snails. All right, so let's get into it here. I'm sorry, just thinking here. In my mind, I'm just thinking of something here. Dun, 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 dun. 0, 0, negative 2. You know what? I'm going back here. I want to check something here. I think I was thinking sine here and not cosine. Cosine, 0 degrees, negative 2. Yep, yep. This right here, n theta equals 90, that's for sine. Ah, okay, this is for sine and not cosine. Here, if theta is equal to 0, if you substitute that in, you get negative 2 times cosine of 3 times 0. 3 times 0 is 0 times negative 2, you get negative 2. So negative 2 comma 0 is on the graph. All right, so I made a little mistake here. I was thinking sine function. Okay, and this is what happens. Sometimes you get things mixed up. If it's sine, then the first pedal starts at n theta equals 90. That's for sine only. Oops. So let me put that down right here. This is for sine only. So I should take this and just move it off to the side. Now cosine here starts on the x-axis. So that's what I did earlier. I don't know what I was thinking here. So at negative 2 comma 0, yeah, here we go. So I'm going to go left 2 units. So we've got to plot negative 2 comma 0, which is here. Okay, not to the right 2 units, but to the left 2 units, because you got to reflect that across the origin. And then your first pedal starts here. Okay, and then you go out 2 units, and then you spread them out by 120 degrees apart. So here, and then 120 degrees this way. So let me see. 90 and 30, it's up here. So 30 degrees up here. So 90, this would be 30. So this would be 120 degrees apart. So go about 2 units up. And then I got to go 30 degrees down this way. This is 30 degrees. 90 and 30 is 120. And then you'll have another pedal length out here of length 2. So let me draw these here. There we go. There we go. Okay, and now they're 120 degrees apart. So this is 120 degrees apart, as well as this. This is 120 degrees apart. Again, for cosine, the pedals start, okay, on the x-axis, on either on the right side or the left side, depending on the a value. If a is negative, it's going to start on the left. How do you remember that? Well, you plug in 0 and you figure it out, okay, when in doubt. And then if it's sine, well, the first pedal starts at n and theta equals 90, and that's a little bit different. So we should probably do one. Okay, so let's go up here and let's grab some space. Let me make up a function here. Okay, so let's say r is equal to 3 sine of 3 theta. Let's do that one because this one's going to be different. So 3 theta here. So n is 3, so we have 3 pedals because it's odd. So I'm going to have 3 pedals. And then a is 3. There's your pedal length. Okay, so let's start graphing here. Okay, also I need to figure out where they start. And as I said over here, for sine function, okay, and this goes for sine, first pedal starts where n theta equals 90. So first pedal starts when n theta equals 90. Now up here n is 3, so we have 3 theta is equal to 90, or theta is equal to 30 degrees. All right, so what I'm going to do here is I'm going to graph 30 degree because I don't have a polar grid. So let's say this is 30 degrees, and this is 3 units. I'm going to rotate, so there's about length 3. And then there's going to be 360 divided by 3, which is 120 degrees apart. So then I go 120 degrees. So 30 and 120 is 150. So my next pedal is over here. So again, they're 120 degrees apart. So I got to go radiate out 3 units. So maybe about right here, I'm estimating. And then let me see, I got to go another 120 degrees, and it puts me down here. Because let me see, so 150 plus 120 is 270, and that's down at the bottom. Okay, and then you sketch. So here, okay, and there we go. And that's for sine. So again, this is for sine only, not for cosine. Cosine starts on the x-axis, either on the right side or the left side. Sine starts wherever n theta equals 90. So let's keep that in our sights. Okay, so remember here, you just saw me just kind of have a momentary lapse of memory right there, but then I checked it. I said, oh, I'm not sure if that's right. I think I've got things mixed up. So then I substitute 0 in. And going back to the previous one here, r is equal to negative 2 cosine of 3 theta. I put 0 in, got the start point at negative 2 comma 0, and that just reminded me of the fact that I got that a little mixed up. All right. So then I redid it Okay, and that's going to happen. So this is a good like example of what could happen to you when you're practicing, because guess what? There's a lot to remember, right? I mean, a lot. All right, but the key thing is like knowing how to approach it. Like what angles do you substitute in to figure out your start point or the pedal length or the max length, and that is like substituting in 0 and pi halves and pi and 3 halves pi to get your maximum length of your pedals and the start points. Okay, so those are the roses right there. Let's go to your limaçons. Okay, now there's 4 types of limaçons. So let's start off with the ones involving cosine, and then we'll jump to sine in a minute. So let's zoom in here and take a look at it. Okay, so cosine first, and there's 4 different types. So I chose a few, 4 of them actually, to kind of analyze. And again, we want to analyze the A and B values right here. So R is equal to A plus B cosine of theta. And then what happens here? Well, let me see, A is 2 and B is 3. And so you want to figure out what type of limaçon you have. And so you need to take a look at the ratio of A to B. And this right here is 2/3, which is obviously less than 1. And when that happens, you have a limaçon with an inner loop. Okay? So that's the first thing I do. The second thing I do is I say, okay, I'm dealing with cosine. And the cosine function tells me about symmetry. And I have symmetry about the polar axis. Okay, so I'm just writing down my thoughts right now of how I'm thinking. So it's got symmetry about the polar axis. Let me see what else. So now I want to take a look at the maximum and minimum lengths. Okay, so when cosine of when you substitute 0 in, you're either going to add or subtract. Okay, and then what you want to do is take A and B and add and subtract them. So 2 plus 3 gives you your maximum length. All right, that's when theta is equal to 0, and that's 5. That's maximum radius. Now to get the length of the loop, okay, or we call it loop length, okay, what do we do? Well, we take 3 minus 2 and we get 1. Okay, also, if you substitute in 0, okay, you can verify things. So if theta equals 0, what do you get for the radius? Well, you get 2 plus 3 times cosine of 0. That's a 0, not a theta. Okay, and the cosine of 0 is 1 times 3 is 3 plus 2 is 5. And so you can see that 5, zeros on the graph. Where is that? Well, let's plot it. Okay, so let's go 5 units out to the right. Okay, now your A value. Your A value is 2. Okay, that tells me that we have y-intercepts up 2, down 2. So I'm going to go up 2, down 2. How can you verify that? Well, you can substitute in pi halves, right? So if theta is equal to pi halves, okay, r is equal to 2. And so 2 comma pi halves is on the graph, and that's up 2. And you can do the same thing with 3 pi halves as well. So if you don't remember all this stuff, you can just do what I'm doing right in front of you, and you substitute in 0, pi halves, 3 pi halves, even pi, and you can get all these values. Okay, so and then we got to plot the length of the loop, which is at 1. So its length of the loop is 1. And then you go ahead and sketch your limaçon. Okay, so here we go. Let me give it my best shot. These are not easy to graph, and it's uh, they're wider than you think, guys. They're wider than you think. So I notice that when people draw these, typically they draw them too narrow. There we go, and there's your loop. Okay, length 1. And that's decent. You know, it's not the greatest, but there you go. All right, and of course you back this up with Desmos. So, you know, split screen and put Desmos on the side, and you'll see it kind of looks like that. All right, but the critical points are the x and y intercepts. Okay, so plot. Okay, the critical points. Plot critical points, and I'm talking about the x and y intercepts. Okay. Those are the important things. And then, you know, give it a decent sketch. Don't make it too narrow, all right? Try to be the best you can. Okay, now on this one here, A and B are the same. So A is 4, B is 4. When A equals B, you have, oh, excuse me, I meant to say B right there. When A and B are the same, you have a cardioid. Cardioid, okay? That's a heart-shaped graph. If I can spell, come on, Aynesworth. Okay, so it's heart-shaped. Okay, and again, you add and subtract b. So 4 and 4 is 8. All right, 4 minus 4 is 0. So it goes through the pole. Okay, this one intersects at the pole. No loop. Okay, no loop. All right, and also when theta equals 0, what do you get for the radius? Well, it's 4 plus 4 times cosine of 0, which is equal to 8. And so 8 comma 0 is on the graph. So if you go out 8 units, I'm going to have to change the scale on this one because I don't have enough room. So let's say that this is 4 and this is 8. Okay, I'm going to plot here. And then A is 4 in this case. So A is 4, and we're talking about y-intercepts there. Okay, just plug in, substitute in pi halves, and you can see what I'm talking about. All right, so we're going to have one at 4 up here, go up 4, down 4. All right, and it hits at the pole. Substitute in pi halves, and you'll, not pi halves, you substitute in pi, then you'll see what I'm talking about. So I'll do that just for funsies here. Let's see, let's substitute in pi. So theta equals pi. Okay, what is the radius? Well, we get 4 plus 4 times cosine of pi. Cosine of pi is -1 times 4 is obviously -4. Let me fix that there. So 4 cosine. And then -4 plus 4 is 0. So 0 comma pi is at the pole, guys. The radius 0. So 0 comma pi, guess what? That's at the pole. Okay, now you draw your cardioid. Okay, it's heart-shaped. There we go. So it's a sideways heart. Pretty cool, huh? All right, and there you go. There's your two limosomes, one with an inner loop, one cardioid, right there, in terms of cosine. And by the way, cosine is symmetric about the polar axis each time. Okay, even the second one is symmetric about polar axis. Anytime you see cosine, that's going to be the case, and that's something that you could have learned in the lesson itself when you were using Desmos. All right, how about this next one? Let's try it out. So I'm just fixing these axes. I don't know what happened here. So just give me a second. There we go. Okay, first one. All right, r is equal to 4 plus 3 sine theta. What's this one look like? So again, we have sine now. So now symmetry is going to be totally different. All right, but we got to check out what kind of limosome we have. So what we want to do is take a look at the ratio. So A divided by B is 4/3, and that's 1 and 1/3, and that's between 1 and 2. So 1 is less than 4/3, which is less than 2, and when that happens, you have a dimpled limosome. Dimpled, okay, like your instructor. Dimpled limosome, okay, or you can say dent. The new phrase is dent. I grew up with the term dimple. I think that makes more sense. You'll see how it looks here in a minute. All right, so where is the max radius though? So you said now sine of theta is max at pi halves. So if theta is pi halves, right, you substitute this in, you get r is equal to 4 plus 3 times the sine of pi halves. Sine of pi halves is 1 times 3 is 3 plus 4 is 7. So we have 7 comma pi halves on the graph. And notice that's up 7. So if we go up 7, 1, 2, 3, 4, 5, 6, 7, okay, plot a point there, that's 7 comma pi halves. Now here, in this case, r is 4, excuse me, a is 4, and when a is 4, we're talking about the x-intercepts now, so it kind of flips, changes from the previous two. On the previous two functions here, a represented y-intercepts, okay, as noted in the first one. All right, when you switch functions, a now becomes the x-intercepts. Ooh, okay. So you got to go left 4, all right 4. Okay, and then you can get that by substituting in maybe 0 and pi, right? So if you wanted to do that, okay, you can go theta equals 0, or you can use pi, whatever you like. Okay, r is equal to 4 plus 3 times the sine of 0. Sine of 0 is 0, times 3 is 0, plus 4 is 4. And so 4 comma 0 is on the graph. So you can see how that kind of plays out. So when in doubt, substitute 0, substitute in pi halves, and then you'll get all these points. So if you forget, don't worry about it. You just substitute in. You can do that in your head. Okay, and then where you got to figure out where your dimple is. So dimple, okay, dimple is located, uh, 4 minus 3 is 1. Okay, so you can substitute in negative, no, excuse me, substitute in 3 pi halves. So if theta is 3 pi halves, okay, you get r is equal to 4 plus 3 times the sine of 3 pi halves. Well, sine of 3 pi halves is negative 1 times 3 is negative 3 plus 4 is 1. So 1 comma 3 pi halves, well, that's down, let's plot it. That's right down here. Okay, so there's your dimple right there. Okay, now let's graph the puppy here. Okay, so here we go. Hmm. Well, I kind of missed that point. It should go right through there. Okay, and there you go. So there's a limaçon that's symmetric about the y-axis now because of the sine. Did I write that down? No. So again, sine, anything dealing with a sine function is going to be symmetric, okay, about the y-axis. It has y-axis symmetry. As you can see, all right, left and right halves are the same. All right, last function here. Let's take a look at what we have. Now again, a is 5 and b is 2, so you take 5 divided by 2, just their absolute values. That's equal to 2.5, and guess what? So that's greater than or equal to 2, and that's my fourth case, and it's convex, and that means that it's got this flat spot, okay? So it's the opposite of concave. So dimples are concave. So if the ratio of A to B is between 1 and 2, you have a concave situation, but we call that a dimple, right? If it's greater than 2, I'm talking about A to B ratio here, greater than or equal to 2, excuse me, A divided by B is greater than or equal to 2, you have a convex limaçon with a flat spot. Now where is that? Well, you add and subtract. So 5 plus 2 is 7, there's your max. 5 minus 2 is 3, and there's going to be your flat spot, okay? But where is it? So I notice that B is negative, so it's going to be, the max is, it's going to be below the polar axis here, but when in doubt, you substitute a point in. So here we go again. So if theta is equal to, let's say, pi halves, where sine's the max, what do we have? We have r is equal to 5 minus 2 times the sine of pi halves. Okay, sine of pi halves is 1, times 2 is 2, 5 minus 2 is usually 3. So 3 comma pi halves is on the graph, which is up here. Okay, so you go up 3. Okay, and there's your flat spot right there. Okay. Okay, what's the max? Well, let's go 3 pi halves. So if theta is 3 pi halves, because sine is max and min at either pi halves or negative or 3 pi halves, what do you get? Well, you get r is equal to 5 minus 2 times the sine of 3 pi halves. So what do you get? You get 5 minus 2 times negative 1. Okay, and that's 5 plus 2 or 7, so r is 7. So that tells me that 7 comma 3 pi halves is on the graph. And then that right there is down 7 units. So 1, 2, 3, 4, 5, 6, 7. It's down here. Okay. And then again, A is 5. A equals 5, and those are x-intercepts. So left 5, right 5. So 2, 4, 5. And then right 5. And then you draw your limaçon with a flat spot. Okay, so here we go. Let's see if I can pull this off here. So I'm going to try to make it flat at the top. Hey, this is actually not too bad. Hey, that's pretty good. I'm proud of myself. Okay, and there you go. And that, my friends, is a fully comprehensive practice session on polar functions with one little slight error in the middle, but I fixed it. Okay, and I'm human. I had a lapse of memory right there. But hey, it's good that you see people like make mistakes, but know how to fix them. That's the important thing. And because guess what? Teachers are human too, and it's going to happen to you, and you have to know what to do and how to adjust and how to substitute in the proper angles like 0, pi halves, pi, 3 halves pi. And you saw me do that in all the different functions here to get the intercepts. All right, and this is right here what you should do and how you should study to get it in your head, because watching me is one thing, okay? It doesn't mean you can do it by yourself. Using Desmos, yeah, it gives you an idea of how things work, but it doesn't get it in your memory, in your deep memory where you can actually remember all this stuff. You have to do, and you have to write, and you have to actually be able to explain it to your classmates easily so that anybody that is listening to you understands what you're saying. And you have to be able to generate this, and you have to be able to substitute angles in like 0, pi has pi, and 3 has pi to get your intercepts and your maximum and minimum lengths. Okay, so practice is the key. Doing the right kind of practice is important, and of course, as you practice here, you can use Desmos to confirm your ideas as you go through it. That's always a good idea, especially if you're making up functions on your own. If you do that, you absolutely have to use Desmos to confirm your practice, because if you're practicing the wrong way, oh my God, then you're getting worse, right? So make sure you either practicing problems that are actually from your notes in your lesson and you're practicing perfectly, or if you do make functions up, that's okay. You better use Desmos to confirm your practice, okay? And this is Mr. Aynesworth here. Hopefully I'll see you in class or in my next video. Take care. Bye-bye.